Greetings, everybody. This next video covers the last topic we'll cover from Chapter 3, and it deals with projectile motion. Um, and then this will take us up to the first exam. Well, okay, projectile motion is, it says here, it's a motion of an object that is thrown or projected into the air, and only uh, it's subject only to the acceleration of gravity. In other words, we neglect air resistance. So the only thing that affects it is the acceleration of gravity, which acts in the negative y direction. So there's nothing affecting the motion of the projectile in the x direction. And we call the object a projectile. The path it takes is called a trajectory. And the trajectory always has a mathematical shape of a parabola. And because the projectile moves only under the influence of gravity, we know that the acceleration and I should mention, of course, projectile motion is two-dimensional motion because it's motion in the x and y direction simultaneously. But because we neglect air resistance, um, well, even if we don't neglect air resistance, the important fact is to remember is that the x and y motions are independent. And thus we can analyze them separately. So it's two-dimensional motion because an object's moving in the x and y direction simultaneously. But we can, those two motions, the x and y motions, are independent. So we can analyze them separately. And again, we neglect air resistance. So they're the only thing affecting the motion, hence the definition, projectile motion. The only thing that affects the motion is the acceleration due to gravity, which acts in the negative y direction. So ax is 0. There's no acceleration in the x direction, and ay, the acceleration in the y direction, is negative g. Again, no different than free fall. Why is it negative? Because g always points in the negative y direction. Okay, well, let's look at projectile motion qualitatively. And here we've got something. It's launched here from the origin. So we've got our x and y coordinate system here. And for all the examples that we'll see, the initial x position will always be 0. We can't necessarily say that about the initial y position, but x initial will always be 0. So instead of an x final, we're just going to have an x, because there's no x initial. X initial is always 0. But y initial may or may not be 0. That depends on the problem. Okay, so what happens is something is launched with an initial velocity we're calling vi. Vi makes an angle of theta with respect to the x-axis. And so Vi is going to have an x component indicated by Vxi. It's going to have a y component indicated by Vyi. Nothing complicated. Vxi is just Vi cosine theta. Vyi is just Vi sine theta. Well, what happens is it's launched, and notice, and this is the best, so this thing is launched into the air, this projectile. It follows this parabolic path, and then eventually it ends up returning to the same height from which it was launched. Well, notice that in this figure, notice that the velocity vector v, the red vector, notice the velocity vector is changing as the projectile rises, because gravity is working against it, causing its y component to slow down. See Vy initial. Then see here Vy at point B is smaller. Notice here at point C, at the top of the trajectory, the y velocity is 0. Then here at D, it's now the y velocity is increasing in the negative sense, Vy. And then right here, when it returns to the same height from which it was launched, we'll worry about Vy in just a minute. But notice here, it's launched an initial velocity we'll call Vi, launched at an angle of theta. Or I guess they call it theta I. I usually don't put the subscripts on theta. If I'm dealing with another angle, I'd call it alpha or gamma or beta. But so what is Vxi? Vi cosine theta. What is Vyi? Vi sine theta. Nothing complicated there, just basic trig. But notice here, and in the sketch we have the velocity at A, B, C. C is at the max height of the projectile. D. Then E is where it returns to the height from which it was launched. Well, let's look let's look at point A, the uh, x component of the velocity vxi. Over here at point B, vxi. Over here at C, they don't have a lid, but it's vxi. Over here at D, vxi. Notice because vx never changes because ax is 0. By definition, acceleration is change in velocity. If a is 0, your change of velocity is 0. So vx never changes, to make a long story short. But notice vy changes. Notice on the way up, the y component of velocity is getting smaller. See vy initial, vy. See right here at the max height, and this is true for the max height, any type of projectile motion, at the max height of that parabola, of that trajectory, vy is 0, and the velocity is entirely vxi, because vx never changes. And then so vy, gravity's working against it on the way up, causing it to slow down. Then it begins to acquire a y velocity in a negative sense on the way down. Now there's a certain symmetry similar to free fall. There's a certain symmetry to projectile motion. You'll hear me a lot of times refer to t up and t down. Well, let's look at points B and D. They're at the same y height along that parabola. Points B and D are at the so I have this horizontal line I've drawn here, and points B and D are at the same vertical height. If I said horizontal, I apologize. I've drawn this horizontal line, and notice it crosses the trajectory at points B and D. So points B and D have the same vertical height and the same y value. Well, notice the time it takes to go from B to C, I'll call that T up. The time it takes to go from B to C is equal to the time it takes to go from C back down to D, because B and D are at the same height on that trajectory. Just like the time to go from A to C, which I call T up. The time to go from A to C is equal to the time it takes to go from C back down to E, because again, points A and E are at the same height. So that's, I call that T. Some of you write TU equals TD, time up equals time down. So you can do that. You can take a horizontal line. Anywhere a horizontal line crosses that trajectory, let me see if I can move it here. Let's see if I can grab it real quick. Well, here we go. Anywhere, wherever that horizontal line crosses the parabola, crosses that trajectory, I like to say TU equals TD, or time up equals time down. All right. And again, Vy is always 0 at the max height. And again, time to go from B to C is equal to the time it takes to go from C back down to D. Time it takes to go from A to C, time it takes to go from C back down to E. Because again, A and E are at the same height, B and D are at the same height. And again, initial speed, initial velocity Vi with an angle of theta with respect to the x-axis. Vxi is Vi cosine theta, Vyi is Vi sine theta. Ax is 0. So we just treat the x and y motion separately. Well, we just have a set of two one-dimensional kinematic equations with constant A. We have a set of equations for the x direction, because remember, we're teaching them, and we can treat them separately. They're independent of each other. So we have a set of one-dimensional kinematic equations for the x direction, set of one-dimensional kinematic equations for the y direction. And we have 4 of them. I've listed them in the blue, written them in the blue here, but we really only have 3. So equation 1, again, left-hand column is x, the right-hand column is y. So we have x equals Vxi times t. Because remember, there's no acceleration in the x direction, and xi is always 0 for every single example that you see for projectile motion. Xi is 0. So you take the general one-dimensional x equation. X is equal to x initial, that's gone, plus v initial t, right there, plus 1/2 a t squared. Well, there's an ax is 0. So that 1/2 a t squared term goes away. Xi goes away because it's 0. You just have x is equal to Vxi times t. Remember though, what is Vxi in general? Vxi is Vi cosine theta. Do not forget that. Now the second x equation, isn't really an equation. It just says Vxi equals Vx, telling you that Vx is constant. That Vx anywhere along the trajectory is the same Vx anywhere along the trajectory, is the same as the initial Vx, because Vx never changes. So that does not help us in terms of any calculations. It's good to know. So we have equation 1, x is equal to Vxi times t. Then let's go to the y equations. Well, again, it's really just the free fall equations. Y final equals y initial plus Vy initial t minus 1 half gt squared. And then Vy final is equal to Vy initial minus gt. So we have 3 equations. I just typically number them equation 1, equation 2, and equation 3. I don't consider this a numbered equation because it's not useful in terms of any calculations. Just remember, if you're looking at the y equation, what is Vy initial? What is Vyi? Vyi is Vi sine theta. You'd be surprised how many students forget that. So right here, what is Vyi? Vi sine theta. All right. And then what is, and again, what is theta? Anywhere along this trajectory. Let's look over here at point D. What is the angle? What angle does the velocity vector make with the x-axis? What is theta? Well, inverse tan Vy over Vx. Yep. Pythagorean theorem. What is the magnitude of V at any point? Pythagorean theorem, root Vx squared plus Vy squared. All right. So really just 3 projectile motion equations that we'll ever need. 1, that's equation 1. It's the x equation. Y final equals y initial plus Vy initial t minus 1 half gt squared. It's equation 2. Vy final equals Vy initial minus gt. That's equation 3. And again, remember, what is Vxi? Vi cosine theta. What is Vyi? Vi sine theta. What is the angle that the velocity vector makes at any point along the trajectory? Inverse tan Vy over Vx. What is the magnitude of the velocity vector anywhere along the trajectory? Pythagorean theorem, root Vx squared plus Vy squared. Okay, let's do an example where we actually toss in some numbers. And so here we have a stone. It's thrown from the top of a building upward at an angle of theta equal to 30 degrees. So the angle with which it's launched, that launch angle theta, is 30 degrees. And the magnitude of the initial speed is 20 meters per second. Okay? And it's launched from the initial height. This says the height from which the stone is thrown is 45 meters above the ground. So nothing complicated. So y initial, the initial height, right there, equation 2, y initial is 45 meters. And then what happens is the person launches the stone at an initial height from an initial height of 45 meters. The initial velocity is 20 meters per second at an angle of 30 degrees with respect to the horizontal. So it undergoes projectile motion, and eventually it's going to come down here, and when it lands, y final is 0. I always set the ground equal to y final. Okay, well, there's a couple of parts to this problem. Part A, how long does it take for the stone to reach its maximum height, y max? Right here. How long does it take the stone? Because here it gets max height. We know Vy is 0 at max height, and then it begins to come back down. So how long does it take to reach max height? Then how long does it take for the stone to land, for the stone to hit the ground? Then I want to know right before it hits the ground, right at that microsecond before it actually physically touches the ground, what is the velocity? I want the magnitude and direction, right before it hits. Well, let's take these in order. Let's look at first, how long does it take the stone to reach the max height? How long does it take the stone to go from here to the very top of that trajectory, that when it's the maximum height above the ground? Well, remember, we know that at y max, Vy is 0. Okay? And this is a very common technique. This is not meant to be tricky. So we want to use equation 3. Okay, how long does it take? I want to use equation 3. So we know that, again, part A, we know that Vy equals 0, y max. Use equation 3 to get t. Vy final, I rewrote it because this is new to us. So Vy final equals Vy initial minus gt. So Vy final equals Vy initial minus GT. Well, remember, max height, what's Vy at max height? 0. So next step, 0 equals Vy initial minus GT. We're looking for T. How long? Very simple. T is just Vy initial over G. Very basic algebra. Now this is where you don't want to get careless. Vy initial is V initial sine theta. If you were just to put in 20 meters per second, you're going to lose points because that's clearly not Vy initial. Remember, this is important right there. Vxi is Vi cosine theta, Vyi is Vi sine theta. Can't stress that enough. All right, so T is Vy initial over G. What is Vy initial? Vi sine theta. The units are all good. Plug in your values as I've done here. You get it takes 1.02 seconds for the stone to reach the maximum height, right here at the top of that trajectory. Okay, part B. How long does it take the stone to reach the ground? How long does it take it the total time from when he releases it to when it lands? Okay. Well, let's use equation 2. And to get T when Y final is 0. And why did I say let's use equation 2? Remember, again, we don't want to overthink it. Remember, this is equation 1, the X equation. This is equation 2, and this is equation 3. Again, I'm not numbering the Vxi equals Vx. It doesn't help us in terms of calculations. It's just telling us, hey, Vx never changes. All right, so we get it. So now I want to use equation 2 to get T when Yf equals 0, because let's look at equation 2. Well, I know Y initial. Okay, I know we want I know Y final 0. I want to know what is the speed it has just at that microsecond before it hits the ground when Yf is 0. So Yf is 0. I know Y initial. I know Vy initial because I know V initial and the angle. So the only unknown in that equation is T in terms of what we have. So here, so that's Y, because to have Yf equals Yi plus Vyt minus 1/2 GT squared. What's Y final? 0. Y initial. Okay. Now this is a common technique. You want to rearrange this so you have a quadratic equation in T. And nothing complicated. I like to make the coefficient of T squared positive. That's just a quirk of mine. It doesn't matter as long as you have an equation of the form, ax squared plus bx plus c, where we just, at squared plus bt plus d. So I brought the t squared term became positive. I'm bringing everything over to the other side, so the t term becomes negative, the yi term becomes negative. Okay, so I get 1/2 gt squared minus vyt minus yi equals 0. Now notice I wrote Vyi in purple because what is Vyi? V initial sine theta in parentheses. Do not forget that. So my three coefficients, 1/2 g, which is 4.9, V initial sine theta, which gives you 10. Remember, V initial is 20, the angle is 30 degrees, and Y initial we know was 45, it is minus, so it's going to be 4.9 t squared minus 10t minus 45. Plug the coefficients into a solver. You get a positive and a negative root. Obviously, the negative root is of no use. So it takes 4.22 seconds for the stone to reach the ground. Part C. What is the velocity of the stone? Magnitude and direction. Obviously, I want the angle and the magnitude just before it strikes the ground. Well, let's look at this figure. So in other words, what is V final at that nanosecond when the height is 0 at that nanosecond before it physically touches the ground? All right. Well, so there's my VF, and I've drawn in the x and y components. There's Vx. There's Vy final. Okay, Vx never changes, so I know that Vx is Vxi, which is Vi cosine theta, which if you plug in the numbers, you get 17.3 meters per second. How do I get Vy final? What is the final y velocity just at this instant? Well, what's the only equation that gives me Vy final? Equation 3. It's the only equation that gives me Vy final. So I'm going to use equation 3. It says right here, we wrote Vy final equals Vy initial minus Gt. So Vy final, remember, what is Vy initial? V initial sine theta. So Vy final equals V initial sine theta minus Gt. Plug in the numbers. We know everything. We know T from the previous part. We know that it takes how long? So we know T when it hits the ground is the 4.22 seconds. So here, plug in the numbers. The units are all good. And you get Vy final is negative 31.4 meters per second. Well, notice, I bracketed, here's my V, here's Vx. Here's Vy final. Remember, at right here, right before the stone physically touches the ground. And I bracketed them, said that Vf is in Q4. Nothing complicated. If the x component is positive, which it is, and the y component is negative, which it is, then clearly your vector's in Q4. Then we're done. Pythagorean theorem gives me the magnitude. Arctan gives me the angle. I'm using alpha for the angle because theta is already spoken for. Theta is the initial launch angle, so I'm calling the angle alpha. Alpha you get, it's inverse tan Vy final over Vx. Units are good, so we're done. And you don't have to do this. It's just a nice, crisp, concise way to write your final answer. Just Vf is equal to 35.9 meters per second at 61.1 degrees in Q4. Alrighty, so that's I'm going to do. I've got the key to the practice test pretty much finished. I'm going to do one more projectile motion example based on that test, or actually two more. Excuse me. Alrighty, let me go ahead and save this file, and let me stop this video.